The Apriori algorithm. One of the most popular data mining approaches is to find the frequent item sets from a transaction dataset and derive association rules. Finding frequent item sets is no trivial because of its combinatorial explosion. Once frequent item sets are obtained, it is straightforward to generate association rules with confidence larger than or equal to a user-specified minimal confidence. A priori is a seminar algorithm for finding frequent item sets using candidate generation. It is characterized as a level-wise complete search algorithm using anti-monotonicity of item sets. If an item set is not frequent, any of its superset is never frequent. By convention, a priori assumes that items within a transaction or item set are sorted in lexicographic order, and let the set of frequent item sets of size k be fk and their candidates be ck. A priori first scans the database and searches for frequent item sets of size 1 by accumulating the count for each item and collecting these that satisfy the minima support requirement. It then iterates on the following three steps and extracts all the frequent item sets. 1. Generate ck plus 1 candidates of frequent item sets of size k plus 1 from the frequent item size of size k. Item set of size k. 2. Scan the database and calculate the support of each candidate of frequent item sets. And 3. Add these item sets that satisfy the minimal support requirement to fk plus 1. A priori algorithm is given in the below figure 1. That is, FL is equals to frequent items of candidate 1, F1, for k starting from 1, and when Fk is not empty, we let k plus plus, and we do the begin of the for loop. First, ck plus 1 is equals to a priori gen of Fk. These will be the new candidates, and for all transactions t in database to begin, ct prime is equals to subset of ck plus 1 t, that is the candidates contained in t, and for all candidates c in ct prime, that is the return of the subset of ck plus 1 t. In the last line, we do the following. We let c dot count plus plus. Then after counting of that, we let fk plus 1 of size k plus 1 equals to the set of c, which is in ck plus 1, such that c that count is greater than or equals to minimal support. That means we try to enumerate all possible subsets as long as the count within the subset is larger than or equals to the minimal support, then we let the frequent item sets to be included in this newly larger ground size of subsets. And in the above figure 1, function apparent gen in line 3 generates ck plus 1 from fk in the following two-step process. 1. Join step. Generate rk plus 1, the initial candidates of frequent item sets of size k plus 1 by taking the union of the two frequent item sets of size k, pk and qk, that have the first k minus 1 elements in common. That is, rk plus 1, which is equals to pk, union qk, which is the set item 1, item 2, and so on until item k and item k prime. Now pk is the set item 1, item 2, and so on until item k. Qk is the set item 1 and item 2 until the set item k prime, where item 1 is less than item 2, which is less than and so on, less than item k, less than item k prime. And the second step is the proof step. Check if all the item sets of size k in rk plus 1 are frequent and generate ck plus 1 by removing those that do not pass this requirement from rk plus 1. This is because any subset of a size k of ck plus 1 that is not frequent cannot be a subset of a frequent item set of size k plus 1. Function subset in line 5 finds all the candidates of the frequent item sets included in transaction t a priori, then calculates frequent only for those candidates generated this way by scanning the database. it is evident that Apriori scans the database at most k max plus 1 times when the maximum size of frequent item sets is set as k max.